So in our next unit, we're looking at what's called constantly accelerated motion. Okay? So what's kind of weird is for the next week and a half, we're only going to study one special case of motion. And that's when something constantly accelerates. So that means you're at a stoplight and you're not moving. Is that constant acceleration? No. Okay? How do you accelerate in a car? What do you got to do? You step on your gas pedal, exactly. And when you constantly accelerate, you keep your foot on the gas pedal the whole time. Now, in real life, a car doesn't accelerate at a constant rate because you have gears and things like that. So that's kind of weird. Like we're spending like a week and a half studying something constantly accelerating. That like never happens in real life. That's just kind of like bizarre, right? So like when do things like constantly accelerate? That like never happens, right? Yeah, I should throw the stapler. That'd be kind of bad, right? Exactly. Okay. Yeah. Usually I run around, I knock stuff off people's desks, but that's just kind of annoying. So free fall is a great example. Okay, that when something is under only the influence of gravity, you have constant acceleration because gravity doesn't kind of pull on you and then stop pulling. That's just weird. Okay, gravity pulls on your body all the time. The other thing that's kind of weird is even though it's like 21st century here, we don't actually know how gravity works. We're still trying to figure that out. And you know that guy with the really bad hair, E equals mc squared? We're talking about Mr. Albert Einstein up into his deathbed was trying to figure out how does gravity actually work? How does every mass, every particle mass in the universe exert a force on another particle proportional to the total mass there? And no one can figure it out. It's just weird. Okay? But we can describe gravity really well. And the guy we got to give credit to first was this guy, Galileo. Okay? And this is actually what he looks like. We got a photo of him. Now, it's just an actor, okay, with a beard and a suit and all that. We're going to look at a short little video tomorrow there explaining this. But here's the basic idea, okay? Galileo was able to figure out how constant acceleration worked by using one of these things. It's just a wooden ramp, okay? And here was his genius. If you think about it, if you drop something, does it fall fast or like fast? What do you think? Yeah, it's actually really fast. We kind of take it for granted. But the acceleration due to gravity is a crazy number. We're going to look at it's 9.8 meters per second every second. That means nothing to you. It's 32 feet per second squared. That also means nothing to you. So here's something that means something to you there. How do you know how fast acceleration is in a car? You look at the 0 to what? The 0 to 60 test, right? Okay? And remember we looked at Mr. Lau's old college car, my 1995 Ford Escort. Woo! 88 horsepower. 0 to 60 in 13.8 seconds. Is that a good acceleration or bad acceleration? Yeah, it's pretty lame, right? That's about a little bit more than a school bus if I floor it. But I have a little trick. If I actually drive off a cliff, there you go, I can actually out-accelerate pretty much any stock sports car you can buy off the lot there. I can go 0 to 60 in like 2.7 seconds is a good way to look at it. About 22 miles per hour per second. So gravitational acceleration, you're like in the ultimate hot rod. You live in an ocean of gravity, but you just take it for granted. Okay? So here's what Galileo figured out. If you drop something, it's very hard to measure. So what he came up with was using an inclined plane, a wooden ramp here. And let me zoom in. So this is Galileo in his workshop. This is actually him now, just an actor with a wig on and like a big old beard. But what he did is, if you actually go to the University of Padua, I think it's right outside Pisa, Italy there, you can visit his workshop, and you can actually see, when you take a tour, these wooden ramps that he used and his telescopes. And what he did is he rolled little tiny balls down the ramp. And what he figured out is what makes the balls speed up down the ramp? Gravity, exactly. Okay? So the hard thing is how do you measure that ball rolling down the ramp? Okay? So you could use some kind of meter stick ruler, which he could have. But the hard thing back then is there's not a good way to measure what? Not a good way to measure time. So you could try using your pulse. But if you get excited, your pulse might be off, right? You could try using like a water clock dripping, but you know, if somebody gets confused and not sure where the bathroom is or it evaporates, who knows, right? So what he came up with was brilliant. He put these little tiny bells along the ramp. And as the ball would roll, it would hit one of the bells. And kind of like a ball falling under the influence of gravity, it would hit a bell. And then it would hit another bell, etc. And all he had to do was adjust the spacing of the bells so that the time was equal, so then they could figure out how far it goes in equal intervals of time. So what if Galileo heard ding, ding, da ding, ding? What's the problem? Two of the bells are too what? Close. What if he hears ding, 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 ding? What's the problem? Two of the bells are what? Too far, okay? And here's what's cool. Once he got the bells equally spaced, he measured the distances. And what was freaky is he always got this pattern, no matter the ramp that he tried. It was always this pattern, which we're going to see in a second. And at first he's like, oh, what happened? Like, why do I get this evil like pattern? Did I sell my soul to the devil? 666, red devils, okay? And when he realizes it's actually the fingerprint of nature, he called it the natural distances, okay? So you know what? His contemporary, Leonardo da Vinci, was really close, but Leo was off. Galileo nailed it, okay? If a ball accelerates 1 unit of distance the first time interval and the second interval, okay, if you're skiing, whatever, right? Are you going to go 1 unit of distance or more than 1 unit as you ski down a hill or go snowboarding? You're going to go what? More than 1 because you're what? Starts with an A. You are accelerating. Turns out you actually go 3 times the distance. So guess what the next interval of distance would be? It would be 1, 3. What's the pattern?
9.
It's going to be 5, okay? Then 7, then 9, okay? Or if you look at it in terms of a free fall motion, okay, Leonardo thought this. Leonardo thought 1, 2, 3. But what was actually correct is you get these odd integer patterns. Or if you add them up, you actually get the natural squares. We'll see that in a second. Okay? So to kind of unpack this for you, he came up with these 4 equations of motion, which if you read about last night, it was probably like, whoosh, okay? But I'm going to show you that these 4 equations actually can be derived from the basic definitions of motion and actually using a little bit of common sense. So here's what we're going to do. Okay? We're going to think about what if, a little thought experiment. What if one day Galileo decides to go skiing, okay, in the Italian Alps here? There we go. So here's Galileo, and I'm pretty sure he didn't really go skiing, okay? This is just a good story here. So please don't go home and tell your parents that we learned about how Galileo went skiing, okay? It's not historical. It's just a way to look at it. And he's skiing down this hill, and just to make life easier here, I'm going to pick a nice, easy number. I'm going to say that he's accelerating down the hill under the influence of gravity at a rate of -2 meters per second squared. Okay? And if the hill stays constant, does acceleration change or is it going to stay constant? What do you think? It's going to stay constant. Okay? And here's what we're going to do. We're going to look at what would happen theoretically for the first, quote unquote, 5 seconds of constant acceleration. Free fall, if you will, pulling you down this hill. Okay? And there's this pattern. It doesn't matter what kind of hill you pick, you're always going to get this pattern. And that's what Galileo discovered. It's a fingerprint of gravity. Okay? So here's what we're going to try to figure out. We're going to try to figure out this thing called VF. You know what VF stands for? That's your velocity what? Final. That's your speed at the end of accelerating down the hill. At the very start, let's just make everything 0. You're not moving. Your V average, that's your average velocity. And then what's delta x a fancy word for? That's your change in your position, your displacement. It's kind of like distance, but with direction. So everything's 0 at the very start. Okay? So here we go. After 1 second, if your acceleration down this mountain is -2 meters per second every second, after 1 second, how fast would you speed up to if you're skiing down this hill? You would speed up to negative what? If it's 2 meters per second every second, it would be -2, right? And why negative? Negative just means we're going which way? We're going down, okay? And in fact, that's usually a sign convention we're going to use to keep things consistent. We're going to call going up positive, going down negative. How about to the right? Let's call to the right what? Positive, and to the left, negative, okay? So in this case, we're just looking at it in terms of going down the hill. That's our frame of reference, okay? How about after 2 seconds? Do you see the pattern? If you speed up by 2 meters per second every second, after 2 seconds, you can speed up to what? You guys okay here? Every second we can speed up by what? By 2. It's going to speed up to what? -4. Okay? Let me zoom in if that's a little bit easier to see. Okay? How about after 3 seconds? What do you think? -6. You guys are awesome. How about after 4 seconds? 8. How about after 5 seconds? 10. That's what acceleration means. Okay? It's a rate of change of a rate of change. On our first unit exam, like a lot of you guys were like that close, and sometimes you just mixed up, is it position, velocity, acceleration, okay? They're related, but they're a little bit different. So some of physics is just getting used to the vocabulary and the ideas there, okay? Next, we're going to look at the average velocity. This is commonly confused with the instantaneous initial or final velocity, okay? Why is this important? We'll see in a second. So how do you find the average velocity? It's pretty simple. The average velocity is just the sum of your initial plus your final velocity divided by 2. If I started off at 0 and I ended up at -2, I'm going to do this in green, okay? What's the average of 0 and -2? Average of 0 and 2 is what? 1, right? You started off at 0, you sped up to 2, okay? By the way, what I'm doing is I'm actually tricking you into using 3 out of our 4 new equations. You're just not realizing it. I'll show you in a second, okay? After 2 seconds, what would your average velocity be? You started off at 0. You ended up at -4. So what's the average of 0 and -4? It'd be what? -2. So in fact, the average velocity is just half your final velocity, isn't it? What's the average of 0 and -6? -3. How about what would be next? -4 and negative what? 5. Okay? So I picked an easy number for acceleration to give us easy numbers as we think about acceleration here. Okay? So now, here's the kicker. Here's the tricky part. This is where the metal meets the pedal. This is to see if you can really put together the physics of how constant acceleration motion works. Okay? Next, we want to find, it's one thing to say how long, that's time. It's another thing to say how fast at the end of speeding up. That's your velocity final. It's another thing to say how fast on average. It's another thing to say how fast you change how fast you're going. That's acceleration. The last question is how far. Usually that's all someone wants to know. Okay? So if you are skiing down a hill and you accelerate at the rate of -2 meters per second every second, after 1 second, how far will you ski down that hill? Okay? Common mistake is to say that, well, you speed up to -2 meters per second. For 1 second, you're going to go 2 meters. That's actually incorrect. Because you start off going 0, you speed up to -2. So you're not moving -2 meters per second until the end of 2 seconds. You see that? Okay? So if he started off at 0 and he sped up to -2, on average, he was only going how fast? Only -1 meter per second for 1 second. Therefore, he will go down the hill 1 meter in the first second. You see that? How about after 2 seconds? After 2 seconds, he sped up to -4. So did he go 8 meters down the hill? True or false? After 2 seconds, if you accelerate down the hill at the rate of -2 meters per second every second, you will go 8 meters down the hill. Answer is false, because that's only at the end of 2 seconds you speed up to -4. On average, you're only going how fast? Negative what? 2 meters per second for 2 seconds. So how far? 4 meters. You see that? So in other words, to get the final distance down the hill, all you got to do is take the time times the average speed. So how about after 3 seconds? You're going to go what? How far down the hill? 3 times 3 is 9 meters. How about after 4 seconds? 16. How about after 5 seconds? How far, guys? 25. Okay? Hey, wait a second. Is there a pattern there? 1, 4, 9, 16, 25. What do you guys see in there? What would be next? 36, 49. What Galileo discovered is a distance you fall under a constant acceleration is proportional to the square of time. Okay? You get an exponential relationship there because you are constantly accelerating. This doesn't seem like that was difficult to discover, but for like, whatever, 3,000, 4,000 years of human history, nobody got it. Okay? So we got to give props to Galileo for putting this all together. So in other words, okay, what Galileo discovered is there's a natural pattern. He called it the natural distances. Every time he tested a ball on an incline, it didn't matter how steep or shallow it was, he always got this pattern of 1, 3, 5, 7, 9. So if you look at something in free fall here, okay, it's the odd integers in successive time intervals, but the total distance fallen. 1 plus 3 is 4, 4 plus 5 is 9, 9 plus 7 is 16, 69 is 25. That's the perfect squares, the natural distances. So here's the kicker. What's the ultimate incline? Is it 10 degrees if you really want to go nuts, if you're snowboarding or whatever, right? Is it 45 degrees? What's the ultimate incline? 90 degrees. You're in pure free fall. Okay? So let's actually put this together for you in terms of how it really looks like if you're totally free falling. So let's say instead of going skiing, Galileo's a total nut. He goes skydiving, okay, which he definitely didn't do, but it'd be nice, right? Anyone ever been skydiving in here? Skydive Chicago? Woo, there we go. That's my dream. One day I'm going to get to go because I'm a physics teacher. I got to go, but I think it violates my life insurance policy, but so does everything else fun, so I'm going to do it. Woo! But anyhow, I'll wait till I have my midlife crisis and I'll go skydiving here, okay? So here's Galileo, and hopefully he's got his backpack on. He's got to have a beard, right? All great Italian scientists have a beard. There we go. He's skydiving, okay? And he's jumping out of an airplane. And we're going to try to measure this. We'll do like a little mini lab, but it's actually very difficult. The acceleration due to gravity has a constant value on Earth. Anyone know what it is offhand? It's just kind of good to know, like how many feet and inches, all that. Okay, yeah, it's negative 9.8 meters per second squared. This is an important number, so we sometimes just call it G for the acceleration due to gravity. Okay, but I like to just call it A because you're used to acceleration. That's all. Okay, this when we talk about it, we might just round this off to 10 to make it a nice, easy number. Okay, but when we calculate, we'll use 9.8. In redneck units in America, 9.8 meters per second squared is equivalent to negative 32 feet per second squared. And if you want to convert that to miles per hour, it's about 22 miles per hour per second. So that's just a good way to look at it. You live in the ultimate hot rod of acceleration. Okay, the Earth is like a super sports car where everything just accelerates towards the center of the Earth. Okay, at like 22 miles per hour per second. So anyway, let's just see how this would look like for free fall there. That's the whole point of looking at all these crazy numbers here. Okay, so hang in there. We're going to tie this all together for you. And we'll do the same exact thing. So if you go skydiving and you jump out of an airplane, woo, this would be awesome. This would be a fun field trip. I don't think I could pull it off there to take everyone skydiving there. There we go. Or for graduation seniors, this would be an awesome thing to do right after graduation there, right? Go skydiving. So you jump out of an airplane. After 1 second, how fast will your body speed up to if the rate of acceleration is 10 meters per second every second? You will speed up to, easy, right? How much? 10 meters per second. How about after 2 seconds? How about after 3? How about after 4? Yeah, how about after, exactly, right? Just every second you speed up by 10 meters per second every second. Technically it's 9.8, but we're rounding it off, okay? So after 2 seconds it'd be 19.6, after 3 seconds, etc. But we're talking about it, 10 is good enough, okay? Now, that's your final velocity. What would your average velocity be? Again, all we got to do is take the average of our starting speed and our ending speed. So what's the average of 0 and 10? It's just what? 5. How about after 2 seconds? What's the average of 0 and 20? It'd be what? 10, right? How about after 3 seconds? 15. So in fact, the average speed is simply half the final speed because our starting speed was 0. Why is that important? Here's why it's important. Okay, I need something to throw. If I got a ball and it starts off at 0, and after 1 second it speeds up to negative 10 meters per second after 1 second, right? It's only going negative 10 at the end of that first second, right? So on average, how fast it was going. If it starts off at 0, it speeds up to negative 10. On average, it's only going what? We just talked about that, right? 5 meters per second for the first second. So how far would it fall? It would fall what in the first second? Would it fall 10 meters or what? It's only going to fall 5 meters, okay? So in other words, if you jump out of an airplane, in the first second, you're going to fall 5 meters. It's about 16 feet, okay? Got it? How about after 2 seconds? How far would you fall? True or false? After 2 seconds, you speed up to 20 meters per second. You're going to fall 40 meters. Does that work? Or it doesn't? It doesn't because you speed up to 20 meters at the end of 2 seconds. On average, you're only going how fast? You're only going what? 10 meters per second, right? So you will end up going, what's 2 times 10? 2 times 10 is 20 meters per second. So in other words, all we're doing is we're just taking the time times the average velocity to get our final distance, our displacement rather, that we're falling. And negative just means we're going which way? Down, okay? So after 3 seconds, we're going to fall how far? 45 meters. That's good. How about after 4 seconds? 4 times 20 is 80, and then it'll be 125, okay? So this is what it looks like in real life, okay? This is crazy, right? And what's nuts is Galileo figured this out like 300, 400 years ago, okay? And again, I want to point out there's actually a pattern here. If we call 0 to 5 1 unit of distance, you see that? Then how much more is 20 compared to 5? It's what? 4 times more, right? How about 45 compared to 5? 9 times more, right? 80 compared to 5. It's 16 times more. 125 compared to 5. It's 25 times more. The distance we fall is proportional to the time squared. Okay? So, how many of you guys think that every time we want to study free fall, you have to make this big table of numbers to figure out what's going on? Would that be really annoying? That would be really annoying, right? Okay? So we don't have to do this, but I wanted you to do this to help you see why we have these 4 crazy equations, okay? And I know this sounds weird, but I kid you not. So like every once in a while, well, Borders and Barnes & Nobles, they're starting to go out of business or whatever, yeah? Or they're out of business already. But they'll have like a teacher discount weekend. If I don't have my faculty ID, I prove to them I'm a physics teacher by writing down these 4 nerdy equations that Galileo came up with, okay? When I need to prove that I'm a physics teacher, I write down these 4 equations, okay? These are called the kinematic equations for constantly accelerated motion. Galileo came up with these. They only work in one special case. What's that special case? When you're undergoing what? Constant acceleration, okay? Which includes free fall there. And he didn't call them this, but we call them the TNEMs, the Nifty equations of motion. They are as follows, okay? Equation 1 is VF equals VI plus AT. Equation 2 is delta X equals VF plus VI over 2 times T, or VI plus VF. It doesn't matter the order. Equation 3, that's a big one. That's a Galileo one, is delta X equals VIT plus 1/2 AT squared. And then equation 4 is VF squared equals VI squared plus 2A delta X, okay? I think by the end of this unit, you'll actually have these memorized like me, but you don't have to memorize them forever, okay? So I actually write them down, and they're like, you're weird, and they give me the teacher discount. Woo, okay? But anyhow, let's unpack this for you. Each of these equations has 4 out of the 5 variables when it comes to constantly accelerated motion, where A is for acceleration, delta X is your change in your position, your displacement, VF is your final velocity, VI is your initial velocity, and T is equal to the time interval of motion. Now notice I created this grid over here, and I came up with this because I actually found it very helpful for my students when we start looking at free fall problems, okay? Notice that in each of these equations, there are 4 out of the 5 variables when it comes to free fall, okay? And one of these is always missing from these 4 equations. So for example, in the first equation, VF equals VI plus AT, notice that it has A, it has T, it has VI, it has VF. What does the first equation not have? It is missing delta X. That's why it's got a little sad face. It's not complete. Oh, okay? So how's this helpful? Here's how it's helpful. When we look at a free fall problem, it's all about breaking down your knowns and unknowns. This is your toolbox of equations to help you attack these ideas here. So once you break down all your knowns and unknowns, that's the hardest part, is reading the problem, sketching it out, listing all the knowns and unknowns. Then you just look at your toolbox to get the job done. If you need to pound nails, use a what? A hammer, right? If you need to put in screws, use a screwdriver, etc., right? You look kind of weird if you're using a banana, right? This is going to help you have success there, okay? When you look at this, how many of you guys think, man, this is a lot of weird, nerdy math? Yeah? Okay? Ha! I tricked you. You actually used 3 out of the 4 equations on our table. Did you know that? Okay? Let me show you. This is straight out of textbook and all that, but what's more important is where do these numbers come from, okay? Let me show you really quick. You actually used all 4 of these equations. You didn't realize this, okay? Check it out. Equation 1 is VF equals VI plus AT. What's the initial velocity? The starting speed was what? Big fat 0, right? Acceleration was -2 times the time, right? So 2 times 1 is 2, 2 times 2 is 4. Use equation 1. Ha! I tricked you. Okay, look at this. You got the delta X. You actually used equations 2 and 3. Did you know that? You didn't even know that. Equation 2, you don't have to write this down. I'm just showing you that you actually use these. Delta X is equal to VI plus VF over 2 times time. The initial velocity was a big fat 0. Final velocity was this column over here. So in other words, it was the average velocity, actually. Right? This is just the average velocity times the time. Okay? You just multiplied column 1 by column 3. You actually used equation number 3. You didn't realize that. That's a biggie. We use this one all the time. Delta X equals VIT plus 1/2 AT squared. Initial velocity was 0. That drops out. Half the acceleration is -2, which is -1, times the time squared. 1, 4, 9, 16, 25. Okay, don't worry about it. You used them. You didn't even realize it. Ha! Okay? So those 4 equations, how did Galileo come up with? I'm going to show you really fast. Writing this down, I just want to show you really quick. Equation 1 is just, this one actually kind of makes sense when you look at it. VF equals VI plus AT. You take the basic definition of acceleration, which is change in velocity over time, VF minus VI over T. You rearrange the cell for VF. You bring the T up, and then you add VI to both sides. So this one, if you look at it, actually makes sense. How fast you end up going, VF, is equal to how fast you were going, VI plus your rate of acceleration times time. Equation 2, you take the definition of velocity, you solve for delta X. Okay? You take velocity as your change in position over time. You bring the time up. If acceleration is constant, you substitute in for delta V. You do a lot of algebra magic, boom, you're done. Okay? Next, number 3. You do lots of nasty stuff. This one, you take equation 1, you substitute into equation 2, you eliminate for VF, and then you have to combine like terms, and you get that one. Okay? So it's just algebra there. We're not going to worry about the details. This one is not very intuitive. And the last one, you have to take equation 1, you put it into number 2, and you do that FOIL thing, the first, outside, inside, last, and you combine like terms, and you get the final one there. Okay? So in the end, it's not using algebra, it's understanding the motion there. So what we're going to do now is we're going to do